Okay, so the recording started.
It's getting recorded.
Okay, so welcome to another session of on CTCI. So today we'll be discussing, welcome to another session of ST skills, and we'll be discussing today the CTCI book, and we'll be discussing the chapter number 5, bit manipulations. Okay, so to start with, as someone suggested last time that we should also go through the theory a bit, right? So let's quickly run through what is in the book and what it says about all this. So, so the first thing in the book, it shows a chart, and this is what this chart is. So the book actually it states that we just go through the chart for as a refresher, right? So how things are done, and I think most of them are not so difficult for all of us, right? We have been practicing these many times.
Yeah.
Okay. So like if 0110 plus the top left one, what it says 0110 plus 0010 actually boils down to 1000, correct? So if we know the addition and subtraction of how we do add and subtract binary bits, okay? So the first column should be easy, right? So should not be a big deal, right? So the second column talks about of multiplications, and we know what multiplication is, right? So if we go through each and every bit, so each and every bit represents two's representation. Like the first bit will always be 2 raised to 0, then second will be 2 raised to 1 and 2 raised to 2 and all that, right? So if we just multiply them, we should be able to get those things. That is also not so difficult. And
Does it work with multiplication, Santos? Because 1 times 1 is 1, right? It,
yeah, that is true. So okay, in this case, if you want to just go that, right? So okay, so this multiplication of the first one, what it says, 0 0 1, right? So if you have 0 1 0, so it will be exactly the way we do in our base 10 also, right? So if I just multiply the first bit, so we just write 0 0 1 1, correct? So now when we are done, so we just skip this position, and now we have 0. So we skip this position also. And then we have another 1 over here. So we just write the same 1 over here. And then if we add them, okay. So if we add them, it is going to be, okay, is it, so will that work? 1 1 1 1 1, right? Or isn't?
it's 15, right? So 3 times 5 is 15. Yeah, that's correct.
It is correct, right? So yeah, this is 3 and this is 4 and 5. Yeah, so 5 15. Yeah, so this is correct.
Mm.
So that is the way, and this one is actually shifting to the right. So okay, we'll come to how the shift operators work in a bit, but what is the most important thing what they have been discussing in this uh, diagram is like the last column. So they say, the last column is slightly different, and there are some tricks involved in this one, and we need to actually understand these tricks. Like if you look at the first one, when it says 0 1 1 plus 0 1 1, right? So it is the same number repeated. Okay. So in that case, we can say 0 1 1 0 multiplied by 0 2, right? It's like twice of this, correct? This is a base decimal. So in that case, when we actually multiply any of this number by 2, we know that if we do use a left shift operator, correct? So we can get it. So if we just have this 0 1 1 0 and then we just shift it by 1, right? So in this case, it will be 1 1 0 0. So this is the way actually we should understand all these tricks. Okay, so this is the one, and in the second one, uh, it says that this is the first number, right? So the first number is 0 1 0 0, which is 4, and multiplying 4 is just shifting two places. So if we shift 0, 0, 1, 1 by two places, right? So in this case, it will be 1, 1, 0, 0, right? So this is the way we actually should understand all these tricks. So usually whenever we have a single bit, it means it is 2 raised to some power. So if we just take that value and just shift it, so then we are good. And in this third one, it says that it is a bit by bit operation. It is this is the XOR, right? XOR, what we have been discussing. And then so any value, if it is negated with its own value, XORed with its own negated value, will always be 1, right? So if we negate 1, 1, 0, 0, so what we will get is all the previous bits will be 0, sorry, 1. This will be 0, 0, 1, 0, correct? And then if we XOR with all of these values, like imagine if it was a 8 bit number, right? So in this case, our original number was this one, right? So this is the original number. And if we negate this number, so this is the negated number, correct? So it will be inverted. All these zeros will be converted to 1. And here also this will be converted to 0. And this 0 will be converted to 1. So, and if we actually XOR this, because XOR of any number, okay, with itself, and if it is an opposite number, it will always be 1. Correct? So here what will happen is we will get a value of all 1, 1, 1, 1, 1. Okay, so this is one. And then the second one actually talks about is if we have this negate of 0, it means if it is an 8-bit number, it will be all 1, 1, 1, right? And then if we shift this by 2, okay, so what we are doing is we are actually pushing these, making these 2 as zeros, right? And so if we add these two numbers, okay, with this number will be the number what we are adding, this guy, okay, if it is here, and if we add them, so in turn what we are doing is we are actually clearing these last two bits, correct? So it will be 1, 0, 0, 0. So this is one small thing. I think we have been using this a lot, right?
Yeah, yeah.
So this
Yeah.
should be not so difficult to understand. Then some tricks about all these stuff. So how is XOR of 0? Okay, XOR of 0 with any number with XOR with 0 will be a same number. XOR with 1 will be actually inversion of that number. Okay, and then if you have any numbers or with all, the same number, it will be 0, right? And the ANDing operation and the ORing operation, right? So these things were easy. And then
Can we look at like the number XOR with itself equals 0, and then we also have the the one on the third row, the number XOR with the gate of itself is equal equal itself. Oh, this is different. Okay, it one is identity, right? The
which one?
third row, on the third row, the number XOR with the gate of itself.
Oh, are you talking about this one?
Yeah, yeah,
The one in the
yeah.
chart?
That's where your cursor is, right?
Okay, this one, right? Okay.
Yeah.
Yeah. So if we have this number 1100, right? And if we XOR with its negated number, oh man, sorry. Okay. And oh, I missed this again. Okay. So if we, okay, so if we have this number, right? This is 1101, right? And if we negate this number, right, so in this case, correct, so it will be like 0010,
One
right?
zero. Okay.
So this is the negation of 1101, correct?
Okay.
Okay, and then he says you XOR with the same number. You XOR with this name number. This is the original number, right?
Mm.
And if you XOR these, so what will happen? 1 of 0, if we XOR this one, so we'll get one value. So 1 of 0 in the second column will be still 1, right? So because they are opposite number,
Mm.
1 and 0, so it will be 1. So it's saying that if we have such case, when we negate and XOR the same number, we'll get all a sequence of all ones.
But it should be 0, right? Because 1101 zoring with 0010. Okay, got it. I took that one. No,
Yeah.
that's correct. Yeah.
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 So if it would have been the same number XORed with same number, then it would have been 0.
0, yeah. Mm.
Right.
So if we want to get it all one, then we XOR with the gate of it, right?
Yep.
And if we want to get 0, and then we XOR with itself.
Yep. Exactly. Yeah. So there are small tricks. Actually, we all know about it. We have been using, but sometimes it's slightly, it is confusing in time. So it's always better to get it properly and cleared before going for an interview. And therefore, I like the way they have given a small briefing in this chapter about all this stuff. Okay, so now this is the 2's complement and the negative numbers. Okay, so we all know what a 2's complement is, right? So if we quickly go what a 2's complement is, okay, I've also not done this for long. So maybe if it is like 0 1 1 1, okay, if this is 7, now if you want to represent the 7 in the form of a, and we just consider only 4 bits for now, right? So we don't go for 16-bit and 8-bit. So if this was a number, okay, and then we had to represent a 2's complement of this. So what would be our 2's complement? So and how do we do? So in 2's complement, first what we do is we negate the whole number. So in this case, it will be 1 0 0 0, right?
Complement. One's complement first you take and you add 1 then, right?
And then we add 1, correct? Yeah. So
Yeah.
then it should be 1 0 0 1, right? So
Right.
in this case, this represents a negative value.
MSB, yes.
Yeah. So and this will be a real value. So here the 2's complement of 7 will actually be -1.
Minus 1.
I
Yeah.
see. Now I understand.
Right.
Yeah.
So this is the way he actually represents these sevens. 2's complement will be -1, and but they are actually, these are not one-to-one correspondences. Okay, therefore slightly not very. They are actually, this is 0 1 1 1, but -1, and then if you see a negative value, okay. So actually, oh yeah, so this is -7 over here. Okay, the -7 value. Okay, this is not -1, but the value is -1, but this is actually the value of -7.
7, yeah.
Yeah. So that is what he's trying to
So
say here.
why would it be -7? Because if we use the first bit to indicate that a negative value, right?
Yeah, the
And
minus.
after that 0 0 1, wouldn't that be like 1? Oh yeah, it is 1.
Yeah,
1.
it is 1,
Okay, got
because
it.
now what will happen? If we take 7 minus 7, okay, it should be 0, right?
Mhm.
So if we just use this 4-bit representation, so this is 7, and -7's representation is 0 0 0 1.
Mm.
Correct. And then
Yeah.
if you add both of them, so 1 0 0, right? So you will get a carry over here. So 1 0 0. So same thing 0, and then this also will be 0. Correct. So and this will be an overflow bit. So we get all zeros. Correct.
Yeah.
So this is the way we use 2's complement when we want to subtract our current number from any other number.
I see. So if we want to convert from negative number back to normal number, we do the reverse.
I think so.
Right.
I don't recollect though. Yeah, but we'll have to do a reverse. But there is some, frankly, I don't know.
Yeah, I
Yeah.
think -1 you do and then again do its complement. You will get the reverse of it.
Okay, we'll try. But yeah. Okay.
Yeah.
So if this is 0 0 1, and then if I subtract 1 from this, so this will be 1 0
1
0, right?
yeah.
And then we reverse it, negate it, right? So this will be
0
0
triple
1 1 1. Yeah,
7.
you're right. Yeah. So we get 0
Mm.
1 1 1. That's right. Yeah.
Okay. I see.
So the way we do it for 2's complement, we actually negate and then add 1. So you are saying that if you want to go from 2's complement of a representation to a positive number, we actually subtract 1 from it first and then negate the number, right?
Yeah. Yeah.
Okay, good. Thanks. So that's a good one. And then if we go, so now they have described about the arithmetic versus logical right shifts, right? So logical shift actually is represented like this, though maybe most of the language implementation they don't show this implementation representation, right? And then we have a arithmetic shift. So there is a slight difference between what is a logical shift and arithmetic shift, correct? So
Yeah.
in logical shift, what it says now, if we have this minus 75 number here, and minus 75, because this is a 8-bit representation of a number, so the first bit will always be 1 because it is a negative number, right? So that is what it's a 2's complement representation here. And then we want to actually logically right shift this. So when we do a logical right shift, if you see in this case, uh, the first bit, actually this bit, see, so this bit is 0, and he has shifted all these bits to the right, and so the first bit from here, so that was the last bit, sorry. So the first bit from here actually is moved out from the whole number, so it is lost. But actually the last bit here is filled with 0. Okay, so that is what its logical shifting is. And then if you go for our arithmetic shift, so arithmetic shift is actually
Looks
arithmetic
like
shift is nothing but we do it like this. So whenever we still do left right shifting, but the last values are filled with whatever the value is over here. So if here it was 1, it will always be filled with 1, and it will keep on filling with 1 the more you do right shift. Okay, or
so if
here it was
originally
0, then it will be 0 again here.
0. Okay. So if it is negative initially, it will be negative, but in logical shift, it can be positive, right?
Correct, yeah, yeah.
Yeah. Okay.
So
But
arithmetic shift, it says it is almost like a divide by 2
two,
always,
yeah. Hmm.
right? Yeah. So
So
but that is not the case for the logical shift.
in C++, they don't have the logical shift, right?
Yeah.
In Python also, I mean, we never use that, I think, in our normal coding.
Yeah, but actually he has the book has been given some of these things, let's go through what the function they are using it.
Yeah.
Okay. Or yeah, but no, I think don't think so. Yeah, we have for all operators. Maybe Java has it, right? Because that is
Might
what
be.
this is a representation of Java. Yeah,
Yeah.
Mm.
you're right. I've never seen that in C++, but
So
it's
let's say in C++,
right.
if you want to it behave like that, what would you do? Like behave as logical shift.
So then in that case, what I would do is you do our arithmetic shift, and before shifting, just mask the last bit, okay, and then always or the last bit with the current number. Yeah. So whenever we do this, okay, before we do it here, we just mask our last number. Say maybe something like mask, okay, is equal to x. Sorry. So x, and then we have a mask of 0 x. It will be 8 0 something like that. We take that, and when we are done with this shifting, okay, so then we again x or with the mask, right? So something if we do that, so it will be, but I'm not sure why we have to do that, right? But is it not we have always, we always use the logical shifting, correct? Oh, we use the arithmetic shifting, yeah, sorry.
Yeah,
Arithmetic
because
shifting. Yeah.
negative is gonna be
Yeah, we always use the arithmetic shifting and not the logical shifting. So it might be required in some cases, so let's see if we require that, then how do we handle it? Okay, so now some of the common bit tasks, what is explained in this book is how to get a bit. Okay, so this is also very simple. If we are given a number as a parameter and then we have given an index, which is I, So how do we get that bit? So we take this I, then we left shift this, left shift 1 by this index. So we are at that particular index, and then we add that number. Okay. So if that number is not equal to 0, okay, if that number is not equal to 0, it means we return true, or if it is equal to 0, it will returns false, right? So that is what the bit representation will be. Okay, so if you want to find what that bit correct particular bit is, and if you want to set it, we also do the same thing. Okay, so we take this number I, then left shift it, and then or with the number, right? And if you go with the clearing the bit, it is again the same. We take this one, we shift left shift with to I by I, and then we, in this case, we negate the whole number. So that will be our mask, right? Because we just want that particular bit to be cleared. And then if we just add that mask, it will clear that bit. Correct. So
Yeah.
then there is something like a clear bits MSB through I, also through 1. Okay, so if you want to clear all the MSB bits through 1, so how do we do that? So we take a mask of this particular number, and then we subtract that by -1, right? And then if we subtract that by -1, and then we or all of them, so we actually clear all those bits. So it's not a single bit clearing, but we clear all the bits from MSB through MSB, right? So if we have, in this case, if we have a number like 0, okay, right. So if you have this number, okay, 0 1 1 1, right? And if you want to clear uh, 0 and 1, right? So if you want to clear something, I was 1, right? Sorry, I was 1 actually. So then how do? We do a mask of I equals, it will be 2, right? Sorry, it should
Yeah.
be 2. So 2, we shift it to 2 in this case, right? So if we shift it to 2, it is going to be 0 0 1 0, correct? And then
Yeah.
if we subtract this number, we are going to get just 0 0 uh, 0 1. Okay, yeah, this is not a very good example though, but and then we actually add that, so we just going to remove all these numbers. But if it would have been 3 in this case, okay, and a number would have been like this, okay, maybe a 4 number, and then in that case we would have come here, right? So this will be a masking, so we'll be removing, clearing all the bits uh, from the end, from this MSB, okay, to the end, right?
Yeah.
And yeah, he has given another uh, so there is another way of actually clearing the bits through 0. Okay, so this is one way of doing it. So in that case, you just take -1 and then shift it by I plus 1, right? So that is one. So there are some utility functions they have described in the book. Okay, I've not gone through all of them, right? But yeah, so it should not be very difficult to follow, right? And the last one talks about updating bits. So if we are given a number and then we are given an index, and then how do we uh, update a bit? Okay, so it's just explained how do we do. So whatever the value of this bit is, okay, so you set that value. If it is true or false, then you set the value to 1 or 0, then you form a mask. Okay, you get the mask, and that mask, whatever the number is, and then whatever the value you have converted from here, the boolean value, we convert to integer, right? So we have to shift that by particular index, and then we just or it, so we'll be updating a bit. So to update a bit, first we have to clear the bit, correct? And then
Yeah.
we put whatever the value will be. Okay.
Could you walk through an example of clear bit through 0?
Okay, so
And
clear to 0. Okay, let us go. Okay, so if there is some example like this, right? 0 1 0 1 1 1 1 1 0, right? So this is our 8-bit representation. Okay, and then if we want to clear something from here, so this is 1 2 3 4 5, and then so our I will be equal to 5, and this is our number. Okay, whatever that number will be. Okay, so then I is 5. So what do we do is minus 1. So minus 1 representation will be what? So minus 1 will be represented as 1
1
1
0
1 1.
All one, right?
Yeah, it will be all ones, right?
Yeah.
So if we have all ones, like if we have an 8-bit one, right, like this, and then if we left shift by 5 plus 1 will be 6, right? So if we left shift by 6, okay, so what we are going to do is we are going to have 1 2 3 4 5 6 almost, right? And so if this is 6, so then we are left with only these two ones, rest all will go away, correct?
Right. Yeah.
Is it correct the way we
Yeah,
do
it is.
shifting? So 1 2 3. Okay, so then in that case, when we come here 1 1, okay, so then will be, I think it should be only 5 ones, right? So if we have, okay, if we just have 1 and then if we shift with 1, so it will be 1, okay, 5, and then we'll be having 6. So maybe I should have taken this index, this would be 5, so it is here, right? That is correct. So I should have taken index as 4 to actually, you know, to clear this. But this is also okay. So we have now 1 and then we have all zeros. Correct. So anyway, we wanted to clear till here. Correct. So that is actually 4.
Mm,
Mm.
0 1 2 3. Okay. 4.
0, 1, 2, 3, 4, and then 4 plus 1 here 5, right? So we are just clearing all of these bits to this place, right?
Yeah.
Bits I 1 through 0. Clear bits 1 through 0. Okay, so actually, yeah, I'll have to look at what actually this says. Okay, so what that says,
Through 0 means what? Like,
okay,
clear
so
bit.
what it says is, okay, to clear all bits from I through
To
1,
zero.
okay, so I through 1 inclusive, we take a sequence of all ones, which is minus 1, and shift it by I. So inclusive I also, right? So if this is 4, so inclusive I will be 5, correct? So 0, 1, 2, 3, 4, and 5. So therefore it says from I to 0. This is I actually. So I means this value. Okay, so inclusive of that value. And if you want to clear all of these numbers, so
Yeah.
how do we do it? Yeah.
That look correct, right?
Yeah. Yeah, I was trying to understand what that function. Uh, yeah. Okay. So I think that's the only thing what they have discussed in the theory part, right? So now if we go through the examples, let's quickly go through the examples. And so the first one actually is a very simple one, and I think we have been doing that in our lead code also. So it talks about insertion. So it says that you are given a 32-bit integer like this, maybe the one which is shown on as an n, input n. Um, and oh, we are given two 32-bit integers. One is n and m, and 2-bit positions I and j. Write a method to insert m into n such that m starts at j and ends at bit I. Okay, so you can assume that the bits j through I have enough space to fit all of m, it's like a valid insertion. That is, if m is this one, you can assume that it can have at least 5 bits, j to I. You would not, for example, have j equals 3 and I equals 2, because m could not fully fit in that. Okay, so that's what it's saying. So it's very simple sum, no tricks in it. You have a value which is given as m, and this is 1 2 3 4 5 6 7 8 9 10 11. Okay, 11 bits represented here, and then we have just 5 bits to be inserted inside that, and from location, it starts from location 2 and ends at location 6. So if you see the output, it shows that, right? It's just odd, that particular number over here. So if you have to do that in this case, okay, uh, so how do we do, right? So it is like this, right? So this number, if you see this portion, okay, so this is what is m, exact m. And if you look at I is I is here. This is a 2 index, correct? 0 1 2, and j will be 3 4 5 6. So j will be exactly over here, right? So this will be I, okay, and that will be j. So we have to just insert this. So for inserting, what I would think is, first we will have to clear this location in case if we had any numbers, correct? So if there were any other ones over here, we just want to clear them first, and just take this value and push it to left by almost by I, right? And then just OR it, right? So it should be that simple. Correct. Or
Yeah.
it should not be that difficult, right? So first we have to clear these bits and then shift M and then merge both of them. Okay. So I will quickly run through that implementation because it's not a very difficult one, right? Oh, sorry, I just made a mess again. So okay, so okay, so this is what is our update bits function. Okay, so my this is n and this is m, and the way what we have to insert is we have to insert m will be a smaller number. Okay, so m was whatever was given here, right? So earlier here n was something like 1 0 0 0 so divided 11 bits, something like that, right? And then m was 1 0 0 1 1, and I was equal to 2, and j was equal to 6. So we come here first, we take this all one, something like that, we just negate anywhere or 0 with itself, so we'll have a series of 1. Okay, and though this will be series of 1, we just actually uh, left shift by 1 plus j. Okay, so if we just left shift all these 1 plus j, so we'll have till 7, right? So 7 till 7 places. Okay, so this, and then all those will 1 2 3 4 5 6 7, so we'll have 7 zeros, right? Okay, and then okay, I'll have to just do this here. And then we actually right shift it by I. Okay, and then we subtract that value. So what we do is we take 1, okay, and then right shift it to 2 0 1 2. So our 1 will be something, will be shifted like this, right? 0, sorry, it will be 1 0 0, correct? Okay, and then if we subtract this by 1, okay, so we will get 0 1 1. Okay, and now if we just or both of these masks, which is the left and right, okay, so then what we will get is something like 1 1 1 1. Okay, if it is that number, and then we have 1 2 3, 4, 5, and 1, 1. Okay, so we'll be able to form a mask. And then if we actually take this mask and apply this to our original n, so we'll be clearing all these 5 bits, right? So they are the 5 bits 1, 2, 3, 4, 5, 6, 0. And then we take whatever this m number and then we just left shift it by I, and then we just OR them. So it's as simple as and what exactly we explained, right?
Yeah.
Yeah. So that was a very simple one, and that was easy to follow too, right? So then the second sum or the second problem is we are given a real number, okay, and this real number is between 0 and 1. Okay, this is not 8, sorry. Okay, I just converted. So we are given a real number between 0 and 1. So example is like 0.72. So we'll always have a what you say, a float value or a double value, and that is passed as a double. So we need to print the binary representation. If the number cannot be represented accurately in a binary with at most 32 characters, we just print error. Okay, so uh, to just give an example, if this is 0.625, so its representation will be like this. Okay, so what does this mean? Okay, so the first bit after the decimal, okay, so that represents it will be like 1 divided by 2, correct? So it is like a 0.5. So then if we go to the next bit, it will be 1 divided by 4. Okay, so it will be 1 divided by 25. 1 divided, oh, so it will be 0.25, right? And then if you
0.25.
go, yeah, and if you go further, it will be 1
8.
divided by 8, right? Yeah, okay. So in this case, if we just see, so the first value will be 0.5, second value will be 0.25, okay, and the third value will be 0.125. And so now if we see that we have only one bit at the first location and the second bit at the third location. So if we add 0.5 with 0.125, so we'll get 6.25. So that was the representation of this float values, correct? And if we have just 0.5, it means it's only the first bit has to be that, right?
Yeah.
Okay. So now if we well, this actually should be 0.1, right? Okay. So then what are our, what is the way to implement this? Any guess?
It's 1 by 2 raised to the power of how many bits you are on the decimal side of it, right?
Mm-hmm. Right. Yep.
And just what do you say, first and last bit you add, that won't fetch
So
it.
okay. So what you're saying is you will be given a float value like 0.72 or 0.65. So
Yeah.
then we have to convert it into this representation in a binary representation. Okay. Is it the other way?
Given a real number, it functions.
So we
I think
do the same way as we like
explain.
you demonstrated, right?
Yeah.
We get convert the one before the decimal first normally, and then after decimal, then we convert it to like, if it's greater than 0.5, we set one bit there. In this case, like right, 0.6 is greater than 0.5, then we set one bit there.
Yeah.
And then we move to the next one.
Right. So, but here the number will always be lesser than or equal to 1 from 0 to
Yeah,
1.
definitely.
Yeah,
Yeah.
it will always be, yeah. So we just have to look only the numbers after the decimal. That's correct. So either he has given two options. One is you multiply the number by 2, okay, and compare it with 1. So like you, if we take 0.625 and multiply it by 1, sorry, multiply it by 2, so you will get some value which will be,
1.3.
yeah, 1.3. And so then you look for that number, if it is greater than or equal to 1, okay, whatever your multiplied number will be, then you say, okay, it is greater than, then you set that bit. And if it is not greater than or equal to 1, so it might be some value which is a float value, right, but lesser than 1. So in that case you just set that bit to 0. So you keep doing this in a while loop, okay, till you don't exhaust all the number. So
Compare
that
by
is why. Could you please repeat that, Shashank?
yeah, I'm saying if it is lesser than 1, then we put 1, right?
No, okay. So what is saying, if you take an example 0.625, right? And then if you multiply this by 2, so it will be something like 1.25,
1.35.
right? So 1.25, you see the value will be 1. So that we have already set over here, right? Okay. So then this actually I subtract 1 from this one now. So what I'm remaining with is 0.25, correct? So
Yeah.
now I'm remaining with 0.25. Then again I multiply this by 2. So I'll get 0.5. Okay. So when I get 0.5, okay, so I know that it is lesser than or equal to 0. So then I just set this bit as 0. Okay. Then I again multiply this number, okay, by 2. Okay. So in this case it is 1, right? So then again I'll set this to 1. And now when I get this 1, again I subtract 1 from this one. So I will get 0. Okay.
Yeah.
So then my while loop stops there. Correct. So this is my binary representation in a string, and then I return this value. So that is what it says when we want to do by via this option 1. We keep on multiplying the number by 2, or else it says is multiply and compare the number by 0.5. Okay. So what we do is we take this first compare we initialize our value with 0.5. Okay, and then we take this 0.5 and we just compare with the 0.625 our value. So if 0.625 is greater than 0.5, right, so then we set this as 1 bit. Okay, and then we actually subtract 0.625, okay, minus 0.5, okay, and then we'll get some value 125. So now we are on the second position, right? So we have moved from 1. So in that case, what we have to do is we have to actually multiply zero point 0.5 by zero point 0.5. So it will be 0.25. Now we have to compare if this number is equal to or greater than 0.25. So it is not. So then we reset this bit. Okay. So then we reset this bit and then we keep on doing our calculations that way. Okay, so the way we do it actually by dividing by 2 is if you see this values, right? It is exactly the same what we do. Okay. So I will quickly run through those two implementations. Okay. So and the first one actually talks about, yeah, so this is the first approach. So what do we do is we take a number here, and if the number is greater than or equal to 1 or less than or equal to, okay, if it is greater than or equal to 1 and less than or equal to 0, we have to return an error because we don't want to do anything for negative numbers and the number is greater than 1. And to start with our binary, or this will be our results, we just initialize with 0 point, and then when we go to this while loop, if we just check if the binary size is greater than 32, because we don't want to run into an infinite loop, right? Because if the number goes more than 32, because we are assuming that it will be just 32-bit representation, we return error, or else we start from here and just first multiply this number by 2. Okay, the way we were talking about the first one. And then whatever the number, like 0.625 multiplied by 2 will be 1 point something, right? So 1.25. So if this number is greater than or equal to 1, okay, you just set this bit to 1 and subtract the number by -1, or else you just set this to 0, okay, and then this number will be same as r, whatever the number was, because it's lesser, right? And then we come again in this while loop and then keep on multiplying the same number, this number, whatever our number was remaining, by 2. Okay, so it keeps on in this while loop, keeps on multiplying by 2, and then we keep on comparing this with 1. Okay, so at the end we just return our binary number. So this is the second way to do. What it says is we have a fraction which is 0.5. Okay, all other conditions are same, there are nothing changed here, but it's only the fraction what we have here. It was 2, but we, in this case, we are taking 5 as a reference, right? So this 0.5, first actually whatever our number will be, if it is greater than 0.5, we add, okay, and then we actually subtract this particular number, like 0.625 minus 0.5, so we'll get 0.125, right? So we just subtract that number. Okay, and in case if it is not greater than or equal to fraction, if it is lesser than the fraction, we don't do anything with that number, we just keep the number as is. Okay, but we keep on multiplying this fraction by 0.5 always. It's like we divide by 2 always, right? So this will always be in multiplied by 0.25 when we actually iterate through this whole loop one by one. Okay, so in the first case it will be 0.5, second case it will be 0.25, and 0.25 into 5.5 will be 1.125, right? So that is the way actually it will keep on going here. And whenever it is greater than the fraction number, only that time you set the binary, set the bit to 1, or else you just set to reset that bit, correct? And you don't change your number in this when it is lesser than that, because it will be a negative number, right? So we only subtract when it is a positive number.
Mm. A small correction, I think it on line 51, when you exclude zero point first, I mean the 32 is exclude, it does not include the zero point, right?
Yeah, you can say. Yeah, so you are saying we can make it something like this, right? 34.
Yeah, maybe like that.
Yeah, that also was fine. Yeah. Well, I just actually it should not be that big also, right? Because if it is 32, somewhere lesser than that, but just picked up some number. And these guys actually are looking for 32 because they don't look for the 0. Yeah, right. So it should be 33 as per them. It is like less than or equal to. Okay, so yeah, 34 is correct. Yeah, you're right. So we just ignore this. Yeah, you're correct. You can do that. Yeah, 34 or equal to 33. Yeah. So even if I run this, and if I just, okay, let me just to see a couple of examples here. This was our binary representation, right? So 0.72 actually doesn't have any implementation, right? Because it cannot be represented by any number, and therefore it will error out. But 0.625 can, and that is what it will be, 101. Right? So most of these numbers, they have to be ending with 5, something like that, right? Because if they have to be divided by 5, 0.5.
5 or 0, yeah.
Yeah, 5 or 0, yeah, correct. Or else then you will always error out. So in this case, you cannot form any valid binary representation. And so this is again for the approach 2. Okay, I'm using the same example, but we can use any example, right? Yeah. Okay, so let's move on to the next problem. Okay, so I think we are almost closer to the, no, we start at 8:13, right? Okay, so we can actually take one more problem, right?
Yeah, sure.
And then we Say, okay. So this is one problem where it talks about flip a bit to win. So what it means is you have an integer, okay, and you can flip exactly one bit from 0 to 1. Okay, so you have to flip a 0 bit to 1, and then write a code to find the length of the longest sequence of ones you could create. Okay, so in this case, if you see one, the input is 1775. It is represented by all these 1 bits. Okay, so we have some zeros also in between. So what it says is we need to flip only one bit, any 0 bit, in such a way that we can form the longest number of ones, right? So in this case, this is the correct one, right? So if I flip this bit, okay, I'll just copy it here. Okay. Okay, so if I just flip this bit, right, the one what is highlighted, so what I will get is this will be the previous to that 0 we have 3 bits, and after that we have 4. So 4 plus 3 will be 7, and including this one will be 8. Correct? So that will be the maximum. But if I flip this bit, okay, so the bits to its left side are 2, and to its right side are 3. 2 plus 3 will be 5, and including this will be 6. Correct? So my answer will be 6, which will be smaller than 8. Right? So therefore, it's always good to flip this bit. So this is what is the problem statement. Okay. So how do you guys have any suggestions of how we could actually do this?
So I think from LSB side, you always do AND operation with one, right? If the result is one, that means that is a set bit, right?
Right. Yeah.
And whenever you hit that 0 and 1 is 0, so try to make that as 1, because it's better to make bit from LSB as 1 rather than MSB, right? Because even if you make from MSB, but somewhere like this, if we make the from MSB side, if we make this 0 as 1, it won't make us the longest one because we will again encounter 0, right?
Well, that is fine, but see, the main problem is like if we have two zeros, right? So either we go from MSB or so. If we just make this one, okay. So
Okay.
in this case, if we were selecting like this one, the previous number, so the number was slightly different. Okay, if we made this one, then we could get all these 8. But if you
Yeah.
had two zeros, what will happen is we have these 4, okay, and then we just have one, so we can only make max here 5, right?
Yeah.
So yeah, that is slightly different of this problem. So what you say is right. We can actually start from one side, okay, and keep looking for how much number of bits we have. But we have to be very careful when there are more than one zeros. So that will
Then
actually change our scene. Yeah.
two pointer approach you can do, like for every two pointer approach, check the number of ones and zeros. And if the number of ones is greater in that than zeros, then try to convert zeros to ones, right?
Correct, correct. Yeah. So
Yeah.
something like that. That is correct. So we just find out. So every time you're saying that you do a sort of two-pointer approach and find these island of ones, right?
Yeah.
Okay, and then you try to see if we can actually club that with the left and right side, and to
Yeah.
club that we need to have only single zero, and if it is not right, then we just add one to it. So in some case it might be true also, like if we have this 5 and this 0, this itself is a bigger number, right? So if we
Yeah.
had only zero zeros over here, in spite of even adding this will be only 5. Okay, or maybe yeah, so if it was 4, so this would have been a bigger number. Yeah, so yeah, two pointer approach sort of yeah should work, but most of the approaches here are slightly different. So let us go through what they say. So what the first approach what is suggested in the book is the integer is made of alternating sequence of zeros and one. Okay, so if you look at this number, what has been done is they have converted this number into an alternating number of zeros and one. So what does that mean is, so this first number, okay, will be number of zeros. Okay, the second will be number of ones. Again, this will be number of zeros and number of ones. So that is what you first create an array, okay, of all these numbers. So now in this, you start with the very first one, the LSB, right? So LSB here is 0. So how many zeros we have at LSB? No, none, right? So therefore we say 0 representation of 0 bits, correct? And then we have 4 1 bits, right? So then we say the second number will be 4, which will be representing number of 1 bits. Then if we come here, okay, so then we have another 0. Okay, so we have 1 0, right? So therefore this is 1. Okay, and then we have 3 ones. So that is what is 3 ones. Okay, then we have only a single 0 here. Okay, then we have single 1 here. And then we have two twos. Okay, so therefore we have two twos, 2 ones here. Therefore the number is 2 here. And then 21 means, because this is a 32-bit representation, so before, prior to these, all are zeros, right? So there will be 21 zeros before that, and therefore this is the 21 value. So now if we convert this number into a binary representation of 0 and 1 alternating ones, so we can just walk through this whole array, okay, and then always try to club. Okay, so every time when we come to a 0, if it is only, in this case it is only 0, so that we can ignore. But if we can go from 4 to 3, so we find 1 0 here. If it is, this number is 1, you see what is there to the left and what is there to the right, you add of them, okay, and keep a max so far always, and then keep on walking through this array, right? So whenever we have more than 1 0, okay, at that time you can just look at the left and right and just add 1 to that, right? So there will be 2 or 3 different cases we have to work on it. Okay, and then we can, because this will actually will be done in O of n operations, or maybe not O of n operations, but it will be based on O of the number of bit operation, right? So that is what it will be. But here we are having an extra space of converting all this into an array, so that can be optimized, and that will be an approach too. Okay, so the approach two is almost like what Shashank was saying. We can actually just use some sort of like a two pointer approach, slightly modified version, and then we can actually on the fly keep on counting them. Okay, every time whenever we get a 1, then we look for the next element. If it is 0, a single 0, then we actually take this value, add to it, make something like a previous and the current, and then keep on adding the values and just keep looking for max so far. So this sum actually is as simple as what we were discussing here. Okay, so let me go through the implementation. Okay, so okay, this is the first implementation, and the function signature is here. So we are given a longer sequence, and this is the n, and if n is equal to -1, we just return the size of 8 bits, right? Because it is as good as all 32 bits. Okay, or else then we convert them into this array of sequences. Okay, get alternating sequence. So this function actually converts this one. Okay, so what it does is it goes through n. Okay, and every time we have 1, okay, then if it is 1, and for searching for, either we are first we start searching for zeros, and then we go to search for ones, right? So whenever we encounter the same value, okay, as for what we are searching for, we don't go in this if condition, or else we keep on incrementing our counter. Okay, so basically we just going through it and just adding our n with 1. Okay, whatever that value is, we the counter what we have counted, we just add to our sequence array, and here is what we actually shift our n number to the right side always by 1, this while loop, and that is the way we convert n into that array of alternate ones and zeros, right? So this is simple. And then when we go here, when we get all these sequences, then there is another function called find longest sequence, where actually the whole thing happens. So now we have these sequence of ones and zeros, the array of that, and then we walk through this whole for loop. And if you see, we are hopping by 2 always, right? Because we know that each uh, what is the sequential values are of either 0 and 1. Okay, so the first value will be always of 0, so therefore whatever the value is a 0 sequence, and the 1 to its right. Okay, so if you go I minus 1, so that will be the right sequence, and 1 to its left, which is I plus 1, will be its left sequence. And once we know what is 0 and right and left sequence, so then it's very easy. Okay, so if our 0 sequence is 1, we know that we have only 1 0, so then we can combine the right and left together along with the 0. So this is 1. So this will be our current sequence. Okay, but then in a scenario when our 0 sequence is more than 1. Okay, so at that case what we have to do is we just look for whichever is the maximum, either the left side is maximum or the right side is maximum, and then we just add 1 to it. Okay, but if our 0 sequence is 0, so this will happen only at the corner cases, when we are at the LSB or when we are at the MSB. Correct. So in that case we just take either the right side or the left side, and then we just go through this whole for loop and always keep on updating our max sequence. It's like the max so far. Okay, so then it becomes very easy, right? So this for loop is very simple.
Yeah.
Yeah, so the one what you were saying, Shashank, about the two pointer approach is here. So because this previous approach we require to convert all these into a vector, that is we were using an additional space, so we can do away with that. Okay, so in this case we come here. Okay, the same base case, so we maintain only two variables. One is the current length and the previous length, and this will be the max length, will be our answer. So any point of time we'll have at least one number, that is what we assume, right? Okay, and then we come here, we have these two values, we go through this R A, and then every time we see if the very LSB is 1, okay, then we increment its current length. And why we do that? Because we are actually shifting our number to the right side always by 1 in this while loop. So first we look for the very LSB to be 1, then we increment the current length. And when we see the LSB of the number to be 0, then we know that we have encountered a 0, right? So in that case, we can look for what was my previous length. So actually we'll have to form previous length now. Okay. So looking for how much if this, then why we are doing 0? Because we want to see if the next value of the A is also 0. Because if we have more than 1 zeros, okay, so then we say our previous will be 0.
Oh,
Correct.
because at one time you can change only one bit. Yeah.
Yeah. Or else if it is not, if it was only single bit, then we actually set the previous length to be the current length. Okay, and then we mark the current to be 0. Okay, and why we do all these previous and current? Because when we come to the max length, okay, when we do the max so far, so we just add previous length with the current length 1. So the way we are doing, right? Because if we encountered only one single 0, then we can add previous and current. Okay, and then we keep on looking for the max length. So every time we just, in the previous case we were having three different cases, right?
Yeah.
Here. Okay, so we were having these three different cases, 1, 2 and 3, but here they have actually merged all of them into one. And the only difference what is being done is we actually update our previous in such a way based on how much value of zeros we encounter at each position. Okay, so we are not worried of how many zeros. If we just know if either it should be 1 0 or more than 1 0. Okay, so if it is more than 1 0, then we always say our previous value will be 0. Okay, and if it is only a single 0, then we actually say our current value will be now previous. Okay, and then we will, whatever the current what we were calculating here when we did not come through this, so we just keep on updating with this max length. So then the problem becomes very easy, correct?
Yeah.
Okay, so this is what the flip one will be like. If we have 1775, then the output will be 8. And then if we have -1, it will return -32. So for the both approaches, we get the same values. Okay,
Yeah.
so I will stop sharing. I think let's wait for now, right? Because we are
Sure.
almost close to the time, and I will stop the recording also. Okay, so we can do the next other
Session.
problem later. Yeah. Okay. Thank you, guys.